Today we're going to talk about periodic trends, atomic size, ionization energy, electronegativity, and electron affinity. We'll be able to explain those things in terms of effective nuclear charge, distance, shielding, and electron-electron repulsions. This pairs well with Quest Periodicity 9. So in honors, you may have learned about these trends already, but just the general relationship, you may not have learned how to properly explain them. AP, it's all about the concept behind why these things occur the way they do. And it gets a little more nuanced when you're looking at the electronic structure of an atom. There's quite a few exceptions that we kind of gloss over in honors, and we're going to really get at the nitty-gritty of those today. The first is the effective nuclear charge. This is a really important argument for explaining periodic trends. It's represented by ZEF or ZF. It's essentially equal to the group number. It refers to how much charge or how much positiveness that nucleus will have. So the higher the ZEF, the more positive the nucleus. The more positive the nucleus, we end up with increased attractive force between the nucleus and the electrons, and therefore the electrons are held more tightly. So if you think about effective nuclear charge for something in group 1, those things all typically form a 1+ charge. That would be the effective nuclear charge. If you're looking at some of the halogens like chlorine or fluorine, we know those things really want to gain electrons, and it has to do with this effective nuclear charge. Their effective nuclear charge is essentially 7. Think about how many valence electrons there are, same in terms of the nucleus. Though that effective charge of 7 is holding onto the electrons very tightly, and in fact it wants to pull more electrons into it so that it is more stable. When we're looking at distance, the distance between the nucleus and its electrons, if that increases, if things get further away, the attractive force goes down, and therefore electrons can be easily removed. If we think about two magnets, if you hold two magnets close to each other but not quite touching, you really feel that tug, but as you move them apart, you're not going to feel that pull as much. Shielding is new. We haven't really talked about that as much, but electrons that are in the core of the atom effectively shield the nucleus attractive force for the valence electrons. Think about the S and P sublevels when we're looking at the core. Those are usually the ones involved in reactions, right? We look at S and P as your valence electrons for all intents and purposes. Think about it like hiding behind someone that's bigger than you. If, say, I have 3 energy levels and I've got 1 valence electron out in that 3rd energy level, I've got 2 full energy levels below it that are essentially distracting me from that electron that's very far away from me. And of course, we're personifying things a bit, but when you go to actually explain, please explain in more scientific terms than that. If the positives already have a pretty good attraction for the full levels, it's going to be really hard to have additional attraction for things that are furthest out or shielded in that sense. This is a good argument when you're talking about going up and down a column. The more energy levels we have, the distance is farther, and we also have more full levels below it, therefore the shielding is greater. So if we think about reactivity, we know that francium is one of the most radioactive, or not radioactive, but most reactive element because it has a very large nucleus and there's a lot of shielding going on. So those electrons are very easily removed from that outer energy level, and therefore it's very reactive. We can't talk about shielding within a sublevel or an energy level due to the orientation of our orbitals. We know that that's where effective nuclear charge takes over when we're looking across. Then we also have minimizing electron-electron repulsions. This one's going to be very important for some of the more nuanced parts of the trends that we'll see. If electron repulsions occur, we can put that atom at a lower energy state if possible, and it will be more stable. Think about the last play posit with that S and D electron rearrangement for silver. we know that 5s level had some electrons that were paired, and we know that the D sublevel had the ability to take on another electron to reduce that repulsion. This electron can actually move over to here. I'm going to draw it big on purpose so we can see that that's the one that moves. It can actually move over into that d orbital, not because the d orbital is more stable, but because we can reduce our electron-electron repulsion. I know that was a little misleading. In the last play posit, I wanted to wait till we got to here to truly explain that. The half-full d orbital, or the potential for a half-full d orbital or a full d orbital, is more stable, but that's not the reason why. The reason it's more stable for those exceptions that we're looking at, the anomalies, is because we are able to reduce our electron-electron repulsions in a farther away energy level. So we know those 5s2 electrons are 1, further away, 2, they're shielded, so the nucleus doesn't have a very strong attraction to them. If we can minimize those repulsions, we will. And since it's for far away, we're able to minimize those repulsions and put it in a sublevel that's a little bit closer and where it doesn't have a pair. This is also important when looking at sublevels like the p sublevel. If I can add another unpaired electron to reduce my electron-electron repulsions, that's great. Once I start adding additional ones, I start getting into more repulsion, and it's not going to be as stable. Okay. So atomic size. When we talk atomic size, there are a couple things we need to look at when we're going down a group. We're looking at an increase in distance, and that is going to lead to a decrease in attraction because we have more energy levels, right? All right. Here you can also use shielding as an argument for the attraction for those outer electrons, but shielding is actually more going to come in with ionization energy when we look at that one. It doesn't explain distance as well, and size. When we look at a family, when we go across a row, this is where Zeph's going to be your primary function here. The effective nuclear charge, as it goes up, attraction goes up, and therefore electrons held more tightly. All right. We also can look at this in terms of ionic radii. So when things exist as ions, just as a general rule, cations lose their electrons to be like the previous noble gas. And by losing their electrons, say if we look at something like potassium, potassium loses that valence electron. The previous noble gas is argon. It's going to have an argon configuration, which is way smaller. So cations typically shrink. Anions typically get larger as they gain electrons. I know this picture doesn't really do justice, but anions expand, and they expand because there's more electrons for that nucleus to attract, and there's also more electron-electron repulsions, so they can go up. We're also going to sometimes have things that are isoelectronic. If you see something that's isoelectronic, that means that they're ions that have the same number of electrons. So if you looked at O2- versus F-, they both have the same configuration as neon there. They have the same amount of electrons, so I'm going to say same E as my definition here, same E. But in terms of looking at the size of those things, we're going to have to default to the effective nuclear charge. Oxygen is more to the left. It does not have as much of an effective nuclear charge as fluorine. Fluorine would be smaller here. Smaller due to Zeph. Okay, even though they have the same number of electrons. All right. So here's a quick example. We've got beryllium 2+, magnesium 2+, calcium 2+, and strontium 2+. The nice thing is these are all in the same group, so as we're going down, we know generally the size will get larger as we go down, but these are all ions, which means they're all in the noble gas configuration. All right. So if they're all in the noble gas configuration, then we're really going to be looking at helium, neon, argon, and krypton, I believe. Yes, I think that's the order. I don't have a periodic table in front of me, so I apologize. Yes, that is the order. So as we go down a group, we are increasing in size still due to energy levels, increase distance due to energy levels, and therefore size goes up as we go down. Okay. Ionization energy. Ionization energy is the energy required to remove an electron from an atom in the gas phase. This always costs energy to remove an electron. This is an endothermic process. Generally, it increases as you go across, and it also increases as you go up. This makes sense in terms of distance. If we look at distance for ionization energy, things that are further away, we can't hold on to quite as well. So if we look at down a family, we know that distance and shielding are both increasing because we have more core electrons. And so our energy, I'm going to abbreviate it E, our energy is going to decrease. So you'll see it's really, really easy to remove an electron from something like cesium compared to things that are higher up in the same column. If we're looking at across a period, so across the period or a row, this is where effective nuclear charge comes into play. Effective nuclear charge, when that goes up, the amount of energy we need to remove an electron also goes up. Now, this is where you can talk about electron-electron repulsions as well. We tend to see some changes. The drop from S2 to P1, this has to do with electron-electron repulsions as well, or the lack thereof. I think S2, we've got a pair here, but then when we look at our P level, that lone electron, it's unpaired. There's no repulsions going on there. It's pretty easy to remove that electron compared to trying to move this electron in the S2. We also could see this issue. You see a dip from my P3 elements to my P4 elements. That has to also do with the electron-electron repulsion. The P3 elements, it's hard to remove those electrons. They're all spread out nicely. They're not bugging anybody. the minute I throw a paired electron in there, it is easier to take this electron because it's naturally being repelled due to the electron-electron repulsions. So that's why we see a decrease from N to O or from P to S, or really anything in the P3 to P4 sublevel. Okay. Now, there's also a second ionization energy or a third ionization energy. So we're looking at the energy to remove the first electron and then each successive electron after that. If you think about the energy levels, if we try to remove something within a sublevel, not too bad, but once we start going to other sublevels or even other energy levels completely, that's where it gets really hard. So like here, magnesium, it's not too bad to remove the first electron. It about doubles for the second electron. And then you see a huge spike when we get to here because we've lost all of our 3s electrons and now we have a full energy shell below it. We've got our 2s2, 2p6. It's going to be really hard to take that electron from the 2p6 because it's a full sublevel, right? And our effective nuclear charge at that point is still pretty high. So we're going to hold on to those electrons tightly. Okay. So why does the energy increase? As you increase the number of electrons removed from the atom, there's several reasons. Again, like we said, minimizing our electron-electron repulsions. We also know our effective nuclear charge plays an effect there. So we got to look at Zeph. We can also look at energy levels. It just gets harder and harder, especially going from energy level to energy level. Right? And we talked about why there's such a big jump in energy level and in energies in certain portions of the table. You see big jumps in energies from the S2 to P1 and from P3 to P4, and then you also see that increase when we're getting to the noble gas area because those things are really stable. All right, so we want to identify each atom, which has the largest first ionization energy, which one has the smallest second ionization energy. All right, so we're going to look at the first one. So we know we've got neon, we've got sodium, and magnesium. So they go in order, which is nice. Just looking at full subshells, I think it's helpful to look at the boxes here, and then I know this is a full p orbital here. All right, so the largest first ionization energy, I could actually rank these. It would be neon, then magnesium, and then, actually, sorry, magnesium would be the weakest. And then sodium, and then magnesium. Reason why, if we look at neon, we know neon has a p subshell that's filled completely. P subshell, subshell is completely filled. So there's several things we can talk about. We know it's a stable noble gas. And we always, whenever we answer this, we always want to compare it back to the other things and why aren't the other things also in play here. So first talk about the atom that you're looking at and then talk about the other one. So we know that sodium and magnesium electrons are from the S orbital of the next level too, the next energy level. So that's a big impact. You know, those things have a greater nuclear distance. So if we're looking at our specific electron, the 2p6 is closer. So we know it's closer to nucleus. We know it's more tightly held. Or actually, we know that because it's closer to nucleus, attraction is greater, right? And therefore more tightly held. And therefore harder to remove. You could even talk about Zeph here a little bit. So consider Zeph. You have a greater nuclear charge, a effective nuclear charge for neon compared to sodium or magnesium, which are group 1 and 2. So there's more positives. All right, smallest second ionization energy. All right, so that one's a little bit harder. So we got to think about which electron we're actually removing here. If we're looking at neon, we'd be removing the 2p5. If we're looking at sodium, we're removing the 2p6 because we've already removed the 3s1. And if we're looking at magnesium, we're removing a 3s1. So the smallest would be magnesium. And we know that it is furthest in distance. So 3s1 is furthest in distance. Therefore, and we always want to compare it, right? Furthest in distance compared to sodium and neon, right? And since it is furthest in distance, so distance is greater, then attraction is less, therefore less tightly held, right? And then energy needed would decrease. So it would be the smallest. Okay. Now, if you were then to try and rank sodium and neon, I would say that the 2p6 electron in sodium would be still pretty tough to remove compared to the 2p5. With 2p5, you'd be reducing some electron-electron repulsions, whereas with the 2p6, you're trying to tap into a full orbital. It probably would be a safe bet to say neon would be the next smallest for the second ionization, but then sodium would be the hardest because it's 2p6, it's a full subshell. All right. Electronegativity, I'll talk briefly about this one. You're not going to see this as much until we get to the bonding unit. Electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. This is based off Linus Pauling's scale. Yes, the same Linus Pauling who, you know, is the password for all of your Namesy videos if you've been there. Things that are more electronegative are more likely to gain those electrons. When we're talking about our bonds, it's also going to affect our polarity. So we're going to have, we're going to really look at this a lot in terms of polarity when we get to the next unit. And these just increase as we're going across, and that's all. They also decrease as you go down. And that makes sense because things that are more likely to be positive don't want electrons. So this is going to be very useful for the overlapping of orbitals when we talk about bonding in the next unit. The last trend, we've got electron affinity. It's the energy associated with the addition of an electron to a gaseous atom. So this is basically forcefully adding an electron to something. So it's the opposite of ionization energy. Things that are about to complete their subshell typically have the highest electron affinity, or most negative, I guess, in this, based on this graph. That's fluorine, chlorine, bromine, and iodine. It's easiest for them to gain that electron. But if we try to force electrons onto other things, you don't see, it's not as favorable. We typically see some issues with electron affinity with these peaks here. And again, those peaks, the reason those occur, you got to think about that transition between the P3 and P4 sublevel parts of the sublevel, or the S2 to P1. Electron to electron repulsions cause a lot of issues with this trend. As we go across a period, it will increase, and that's due to the increased ZEF, or nuclear charge, and we have greater attraction for those electrons. And that is all for today.